Hello, Calculus 2 students. Today we're going to continue looking at sequences and whether those sequences converge or diverge. So we've got 3 examples. So my class today started by considering each one of these examples and using them as a warm-up, and trying to think about them as many ways as possible. For the 3rd example, you actually need to, just like we did in Algebra 2, actually build a sequence expression for it first and then use one of our strategies to determine whether it diverges or converges. So if you're watching the video, I'd highly recommend, if you've watched the first one, that you now pause it and try to work out whether these sequences diverge or converge. So, what do we get for the first one?
I got that it diverges.
It should. It does diverge. So, let's talk about why that is. How did you girls do it this time?
I just figured, I set up the limit as n approaches infinity.
Okay, let's set that up. So we're going to look at the limit as n approaches infinity.
I decided that the top grows faster than the bottom.
And then you use an order of magnitude argument, huh?
Yeah.
So the top does grow faster than the bottom. That's linear order of growth. That is square root order of growth. So if you wrote that in a sentence, that would tell you that this limit comes out to infinity, and hence the sequence diverges. Okay? Technically, let's remind ourselves that the reason this works is because we have a theorem that says as long as the sequence matches up with the relevant function. Really, I shouldn't have n's in this. I should have x's. It doesn't really matter too much. I mean, you can write it either way. But because that sequence matches this function for all of the natural numbers 1 to infinity, since this limit equals infinity, that sequence will do the same thing, have the same behavior. It's a little technicality, but it is kind of important to realize the distinction between sequences and functions. Okay, so I also want to show this one algebraically, if you wanted to show that algebraically, because right now this is kind of a wishy-washy statement unless you write out a couple sentences. How could you show it algebraically? You guys have any suggestions on that?
L'Hopital.
You could use L'Hopital's rule. That'd be a great way to do this limit. How else could we do this limit? Clever algebra. How do you kill x? Divide by x. If you do something on the top, what do you do on the bottom? Same thing. So that would work out to this. So we get 1 on top, and if we stick that 1 over x inside the square root, what's going to happen? It's going to become 1 over x squared. So this is going to be x over x squared, like this. And you're going to have 1 over x for that term. And then what are you going to have here? You're going to have 7 over x squared. Now as x tends to infinity, what's going to happen? Well, 1 is 1. Square root is square root. 1 over infinity is going to go to 0. And this is also going to go to 0. So that's kind of weird. So it's basically like you have 0 here. But remember, in limits, we don't just think of plugging in, we think about approaching. So this is 1 over something really small. So that's going to be, let's write it out the way we're used to. Really big, which is going to go to infinity. Okay? So there's a really nice, more formal argument for why that sequence of numbers diverges. So, how about b sub n? Does this one diverge or converge? What did you guys say? Diverge?
I was thinking
I think this one converges. Let's write out some terms. That's always a good strategy if you're not sure, especially if you don't know what strategy to apply. One of the first things you should always do is just write out some terms. So what would b sub n be as a list? If we plug in 1, what do we get? This is an alternator, right? That makes you go positive, negative. So if you put 1 in, you get squared, so it's positive. 1 over 1 squared is 1. Okay? If you put 2 in, cubed, negative.
Negative 1/4.
1/4. Put 3 in. It's going to be back to positive because 3 plus 1 is 4th power. 1/9. If you put 4 in. So if you visualize what this sequence is doing.
It's oscillating.
It's oscillating, sure. It's oscillating above and below the axis, right? But is it actually converging to something? Something that's oscillating could still be converging. At 1, it was 1. Then at 2, it's negative 1/4. If this is negative 1, now it's here. At 3, it's at 1/9. That's a lot closer. and at 4 it's at negative 1/16. That's a lot closer. Does it seem like it's converging to something? My instinct tells me yes, this is converging to 0, right? How can you show that? This is actually a convergent sequence.
Use the squeeze theorem.
Squeeze theorem is the way to do it. Very nice. So this guy is convergent by the squeeze theorem. Now, if you were in a higher level class, that'd probably be about all you'd need to write, because anybody on a higher level would just look at this and go, oh yeah, squeeze theorem, I got what you're saying. You guys know what I'm saying? At this point, we probably want to be a little bit more formal. What is this, in fact, squeezed between? What two other sequences can we squeeze this alternating one between? So we've got this guy with the alternator over n squared, can be squeezed between what two other sequences? Well, it can be squeezed between 1 over n squared here and negative 1 over n squared there. If you picture what those do, 1 over n squared is going to go like this as you go out to infinity, and negative 1 over n squared is its reflection. This guy is always bouncing around in between there. And that's got to be true for all n, or at least for all n greater than some stopping spot out there, but I think this one's even true for every single n value, that it's greater than or equal to. In fact, a lot of these times it's actually on the edges, right? It's going like this. But since that's true by the squeeze theorem, this converges. That squeeze theorem then gives you one of the main other theorems in our book, which is the idea that has to do with absolute values. So I think this is a great problem to talk about that theorem on. So there's a theorem that says if you have a sequence that's absolute valued, if that guy converges, basically, then what must be true? Then the regular thing also converges. This is, of course, not going to be true for series when we study those, but it is true for just lists of numbers. Why? Well, the proof is basically the squeeze theorem. If you have a sequence, any arbitrary sequence, what could you always squeeze it between? You could squeeze it between that and negative that. That would always be between positive and negative of itself, right? So that's basically the reason that you can do this with absolute values. And that picture below also kind of explains that pretty well. So that's the idea. Let's look at our third warm-up sequence now. So on this one, it's a little bit tougher pattern than most of my Algebra 2 students would do. What is this guy? I'm going to call it C sub n for our third sequence. I think the telling part is 6, 13, 22. Those look really familiar. I think those are close to our square numbers being like 9, 16, 25. So each one is how much different from our square numbers?
3.
It's going to be 3 different, 3 less. On top, you have to know your power as well. This is one of the reasons I train you in power tables from the very beginning, is so you can catch these, because otherwise you'd be kind of out of it. So what do these look like? They look like powers of 4, 16, 64, 256. These are all almost the powers of 4. They're just each one more than the powers of 4. So I think that is an explicit way to write down that sequence versus a list. The other form of writing down a sequence is what? You guys remind me? How else could you write it down? We're not going to use it very much, but recursive, very nice. So anyway, once we've got it explicit, we can take a limit or use the squeeze theorem or use any of those tools. So the limit as n approaches infinity for this guy is going to be what? It's going to be infinity, let's say, since exponentials,
Grow faster than squares.
yes, grow faster than polynomials. Specifically, in this case, square polynomials. So that means that this sequence diverges. Okay, there we go. let's look at now another tool by which we can conclude whether sequences diverge or converge. This tool is very different. I think you're going to think about it as very new. It's also kind of the groundwork. It's laying the foundation for advanced calculus, in other words, analysis or much higher level math. So we're not going to use it a whole lot in AP this year, but it is something we definitely want to introduce at this point. Some neat ideas and also frameworks for that higher level math. So let's look at that now. All right, so another tool for determining whether sequences converge or diverge doesn't involve limits at all. It's a little more analytical, so it's more about inequalities and so forth. So basically, this tool works by looking at two ideas: whether your sequence is monotonic and whether your sequence is bounded. If it's both those things, then it converges. Bottom line. It does not work like this, so it's tempting to think like this. It does not work by you thinking, well, it wasn't monotonic, so it diverges. It wasn't bounded, so it diverges. This is going to be the way that a lot of ideas work moving forwards in Chapter 9 for the rest of this year. If a certain method, a certain tool fails, that doesn't mean you can conclude the opposite of what the tool tells you can do. It just means that the tool failed and you need to pick a different tool. Does that kind of make sense? So I think that's a temptation with this one. We'll look at 5 different sequences. We'll try to use the tool on each one. It might not work on all of them, so we'll fall back on other strategies otherwise. Okay, so what does monotonicity mean? Monotonicity means basically what it sounds like. It means that you're strictly or only increasing or decreasing. That's what it means to be monotonic. Bounded means that you're stuck in between two values. For instance, this sequence that I've drawn on the board, at least those terms that we can see, is bounded. If it goes above any specific bound at some point, then it's not bounded. So it has to be bounded both above and below in order to qualify as being bounded. Okay? If you can establish that something is strictly increasing and bounded, well then of course it's going to be like strictly increasing to the thing it goes to. So of course then it converges. Same thing, if it's strictly decreasing and bounded, then it's going to be like strictly decreasing down to something specific, and that means it's converging to that thing. So this is a very, I think, commonsensical idea, but it's also quite formal. So let's remember that. So now we want to evaluate these sequences and decide, using everything we know. What is this sequence doing? Alternating, right? A good thing, always just write out a few terms, right? So if I write out the first term, if I put 1 in, that's squared, so I'll get 4, right? If I put 2 in, that's cubed, negative, so 2. If I put 3 in, it's to the 4th power, so it's going to add 1, so it's 4. Isn't it going to keep doing this forever? So technically, is this going to converge or diverge? From what we learned last time, even though it doesn't go to infinity, it's still diverging because it doesn't settle down to one single value. So this is divergent. It's divergent according to those previous ideas. Now let's think about, does it qualify as monotonic or bounded? Well, is it bounded first of all? Well, it's clearly bounded above by like 4, or you could even just say 5 and be extra safe, right? You could say it's bounded below by something like 1, or you could even just say 2, right? So it's bounded. Is it monotonic? No, because it goes down and then it goes up. And that makes sense that it came out to be divergent. But just because it fails the test, like this one failed the test, doesn't mean it has to be. We had to use our other idea of divergent on it. Okay, what about this one? What do you guys think? Let's use our limit ideas first. We'll kind of cheat. You think it's going to converge or diverge? Do we need to write out the terms?
Converge.
I think it's going to converge to. Why?
Converge to 2.
It's going to converge probably to 2 because the limit as you approach infinity goes to 2. You can think about L'Hopital, order of magnitude, whatever you want. So I agree. I think this one's going to converge. But just to get familiar with our new tool, which might be the only way to go sometimes, and which gives us a little foundation in upper level mathematics, let's show that it's monotonic and let's show that it's bounded. A first good step might be, once again, write out some terms just to get comfortable. So if I plug in 1, I get
1.
2 over 2 is 1. If I plug in 2, I get
4/3.
4 over 3 is 4/3. If I plug in 3,
3/2.
4, 6, 6/4, or 3/2. and so forth, right? Maybe I need to work out a few more terms. If you're getting stuck, write out more terms. Okay, so
Strictly increasing.
what do you guys think? How can we show that it's bounded? I think you'd probably want to write out a sentence and say something. I don't think we have the other analytical tools yet, but basically it's bounded because
It can't go below 1.
there's 1. Is this going to keep getting bigger than 1 or smaller?
Bigger.
I think it's getting bigger slightly, and you could establish that even by like maybe turning these into decimals just to see a little bit. Going like this is like 1.33, this is 1.5, and do that with a few more terms, and you'll see that it's clearly always going to be bigger than 1. So we know that it's bounded by 1 below. Is it bounded above? Maybe we need to write out some more terms. But you guys already talked about the limit, right? Maybe we could use that limit. No matter what, isn't it going to keep getting, looks like it's going to keep getting bigger. We haven't proved it, but it's going to be bounded above by 2. So I really haven't proven these two statements, but I've got a pretty good idea about them, and that's what we want to be at in BC Calculus. How do I show that for sure it's increasing or decreasing? There's multiple ways to do that. What shows whether something's increasing or decreasing? What tool that you've learned in the past in Calc 1? Derivatives. So you could take the derivative of that function and show that the derivative shows after 1 that it's always positive. That's one way to do it. We'll be doing that sometimes this year. I think this time I'm just going to use an inequality. So I'm just going to see b sub n compared to b sub n plus 1. If it's increasing like we expect, and it strictly does that, then this has to be which way?
Less than. B sub n has to be less than.
Yes, right? Do we know this? I don't think we've shown it. Let's show it. We're going to have to show this in lots of situations. So b sub n we know is 2n over 1 plus n. How do I do b sub n plus 1?
2 times quantity n plus 1 over 1 plus, or 2 plus n.
Yeah, right, just like that. This is a very familiar argument we're going to be using lots of ways, so might as well get used to it now. Looks like it's true, but that's certainly not proof. I still don't know, so I'm going to put my question mark. I'm not sure yet, right? What could I do to try to manipulate this into something that's obviously true?
Solve for n.
Try to solve for n? How?
Cross multiply.
Cross multiply? Okay, cross multiplying I think would be a good idea. I also see something with factors up here. Do you guys see that?
Yeah. And then,
So then when we cross multiply, we'll get 2n times 2 plus n less than or equal to 2 times that same quantity squared, right? So I think I'm just going to distribute now and see what happens. 4n plus 2n squared. This is going to be 2 times n squared plus 2n plus 1. So that's 2n squared plus 4n plus 2. Ooh, that's already almost on the other side, isn't it? So when you're working with a statement like this and trying to show that something's increasing or decreasing, just play with it. It'll come out if it's true. Goodbye, 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 goodbye. I can subtract those. They're on both sides, right? So what's left over here?
0 is less than 2.
So notice, I didn't know this, I didn't know this, I didn't know this. Yes! So technically as a proof, if you're writing this out proof-like, you'd have to say, okay, first I know this. If that's true, this is true because of clever additions. If that's true, this is true because of factoring. If that's true, this is true, factoring, undistributing factoring, right? If that's true, this is true by weird rearrangement. If that's true, this is true. If that's true, this is true. This is a proof, basically, that b sub n is strictly increasing. So by the theorem, I could say since it's bounded and monotonic, it converges. Okay? There's a little taste of advanced mathematics for you. I know it might be a little bit weird, but it's so much fun once you get good at it. Okay, c sub n. Let's try that one. So what do you guys think?
Converges to 0.
I think based on our old rules, we have that it converges So let's see what happens with this testing stuff.
1 over 1.
So let's just try to show, does it decrease strictly, increase strictly? What would be the first step to that?
You could do the inequality like we did before.
We could try to do the inequality.
Plug in some ends first.
We could also just like plug in some ends. It's always a great idea just to get yourself oriented, to get your feet wet. So if I plug in 1, what do I get? 1 over 2 minus 1 is 1. If I plug in 2, I get 4 over 4 minus 1 is 4/3. If I plug in the next 3, I get 9 over 8 minus 1 is 9/7. Let's plug in one more. Then we're going to have 25 over 2 to the 5th is what?
6.
Or I'm plugging in. I'm plugging in.
the
Wrong. 16.
Yeah. 16 over
16 minus 1?
yeah, over 15.
15. You guys help me turn those into decimals?
Oh, it's like increases and then it goes back closer to 1.
Ah, see. This is 1, 1.33. What's 9/7?
1.29
16/15.
is 1.07.
So, notice this guy increases and then starts decreasing. I think it decreases from that point out, but that shows that it's technically not monotonic. So we're going to say this guy's not monotonic, but even though it's not monotonic, does that mean it's not convergent?
No.
No, that just means it failed that way, that tool. It failed that ability to detect whether it was convergent. If we take the limit, we know that this grows much slower than that, so it's going to go to 0. This thing, in fact, converges. So I'm going to say no, but it's still convergent. Why am I being so picky about these tools? Why won't we just use the most efficient tool? Well, I want you to get used to using a tool and that tool failing, and what you do when that tool fails. So that's what a lot of Chapter 9 is going to be about. Anyway, how about d sub n? Clearly the limit goes to 0. Let's show that this is in fact with the tool. Show that it's convergent, I should say, converges.
1/4, 1/6.
That's pretty clear, so let's write it out as an inequality. Is d sub n less than d sub n plus 1? Well, d sub n is this. Is that less than this? Yeah, I don't think I need to do anything more. Check mark. I could even just say, if I wanted to be super explicit, any higher level math, you'd never do that because it's duh. But bigger denominator, right? Bigger denominator is clearly a smaller thing, okay? So that guy is clearly monotonic.
Wait.
If it's a small,
It's strictly decreasing, not strictly increasing.
that should
So
be flipped.
it should be switched. The inequality sign.
This thing is getting smaller, right?
That
No,
thing
it's
is bigger
bigger
than
than-
the one after it.
because as the denominator increases, the
Thing gets smaller.
Yeah.
So this thing should be smaller.
yeah, so it needs to be less.
So it just
I'm
needs to
talking
be
about it
flipped.
right, but I have my symbol backwards.
Yeah.
Okay, thank you. Good job, girls. Yeah, totally. I was talking like this, but I didn't have it written like that. Very nice. So, there we go. So it's monotonic, right? What's it bounded by? Be nice if I had the terms written out, but what's the biggest it can possibly be?
1.
1, and then it decreases from there.
And
So
0.
I'm going to say bounded by 1. What's the lower bound?
0.
0. How come you know for sure that it's never going to touch 0?
Because that's undefined.
We've known that forever, right? You can't have 1 divided by something being equal to 0. That is the definition of undefined. Very nice. So I think that would be not a rigorous argument, but a good one. Okay, last one. What do we think? Convergent, divergent? Divergent. Divergent because that grows faster than that if we did it with a limit. What could we do thinking like this? Is it going to fail? Which one? It's got to fail at least one of them, right? Is it bounded? We could start writing out the terms. The terms go
1/2, 4/3,
3 is 9/4,
9/4,
4 is 16/5, 5 is 25/6. Running out of colors. 0.5, 1.33, 2.25, 3.2, 4.17.
Yes.
Doesn't look like it's bounded to me, so it fails to be bounded. We could also check to see if it's monotonic, but I'm not going to. It already failed that, so we know we can't use the test. Only the limit thing showed that it was divergent, though. Does that make sense? You can't use the test and say, oh, it failed being bounded, so it's not convergent. You don't know that yet. It just failed the test. So that's the idea. One last thing, one little tool. We're going to start working with factorials more and more. You saw those in the first lesson video. So let's look at simplifying some factorials for when we need to show something is monotonic when we have factorials in there. So just some simple factorial calculations. I thought we should think about first basically what is a factorial, then we'll take it to variable end, and then we'll take it to something more interesting. So, how do you figure out 7 factorial?
7 times 6 times 5 times 4 times 3 times 2 times 1.
Okay, but we're not going to be working with factorials like that usually. You could cut this off at any point, right? You could say it's 7 times
6 factorial.
6 factorial, or it's 7 times 6. In other words, 42 times 5 factorial. There's lots of ways to manipulate factorials. So n factorial can be written as n times n minus 1 times n minus 2, or it can be written as n times n minus 1 factorial, or it can be written as n times So how do we write out 2n plus 3 quantity factorial?
2n plus 3.
If we wanted to expand it as much as possible, we could start with that and then go
Plus 2.
Or 2n plus 1.
and we could stop wherever we needed to for our simplification desires. So what I wanted to do this for is because you're going to need to be testing stuff. You're going to have stuff like this in your sequences. If this was in your sequence and you're trying to test whether it's monotonic or something, what are you going to need to do? You're going to need to do something like plug in n plus 1 to get b sub n plus 1 or whatever, right? So how do you do that? You go just like that. So what is that?
2n plus 5.
Which then you could write as
2n plus 5 times 2n plus 4 times 2n plus 3 times 2n plus
And the reason you might want to stop here is because you're probably going to be comparing that to the original on the other side, and maybe you get that to cancel out or something like that. So there's some basic mechanics with factorials which are going to serve you well throughout the rest of chapter 9. See you next time.